Welcome everybody to today's FDTD Satellite Applications webinar. Today we're very pleased to have Dave Zapp from the Weather Service office in Buffalo, New York. He will be talking about one of the big lake effect snow events they had this year back in November. Next slide, please. A reminder that all of these chats are recorded and made available on the visit web pages at the URL shown here, so you can check these out as you please or share these with other people in your office. Also, we're looking for speakers. If you'd like to speak on a topic related to operational use of satellite imagery, please get in touch with either myself, Dan Bicus, or Scott Lindstrom. Our emails are listed here. Next slide. We'll have about 20 minutes for our speaker today. If you have any questions, you can put them in the go-to questions in our go-to meeting, and then we'll have a Q&A period at the end of this as well. Just remember, don't press hold and mute when not speaking. At this point, I'll turn it over to Dave.
All right, thank you, Dan. So yeah, my name is Dave Zapp. I'm the Science Operations Officer here in Buffalo. We've had a number of interesting events in the Buffalo area this year. The first one is the one I'm going to talk about. It occurred between November 17th and the 20th of 2022. It was a classic lake effect event. The one I'm not going to talk about is the event that occurred near Christmas, which was a nothing short of a historic blizzard for the area. I'd love to discuss that from a satellite perspective also, but for a good portion of the time, we had a lot of cirrus overhead, and there just isn't a lot of neat features to look at. This one has all kinds of neat stuff to show, so I will do that now. Some of the things I'm going to talk about are 4 shortwave troughs that pretty much dictated where the lake band ended up, and you can see that on channel 10, or the mid-level water vapor. We'll look at several loops and some still images of day cloud phase distinction. We'll look at one loop of the day snow fog RGB. We'll look at some nighttime physics RGBs, or RGB. We'll look at some VIIRS imagery. Particularly interested in looking at the convective roll clouds that you can see from all of the above. And a few different loops with some of the geostationary lightning mapper, or GOES lightning mapper, and then one image of some new caps data. The images down the bottom were taken at my home between my wife and myself. We didn't really intend to do a classic outdoor picnic table shot, but this is what sort of happened. It was just amazing to see how quickly the snow was accumulating. And no, I didn't measure the snow on the top of the table here. But yeah, you can see at 7:30 we already had, I think we had about 17 inches of snow on the ground by this time. By 3 in the afternoon, you can see the chairs are mostly covered, and by 7:30 in the evening, the entire outdoor furniture set is covered. And the picture on the right is of my neighbor's house, because my neighbor's house is much more scenic than mine. But you can see 45 inches of snow roughly in 24 hours. Some of that, of course, had settled. But just an amazing dump of snow. I can't think of many other words to describe it. So for those that aren't too familiar with lake effect processes, I'll just do a quick overview here. You need a cold body of a cold air mass over a warm body of water. That's your classic setup. That'll develop the steep lapse rates that you need for rising motion. From that absolutely unstable environment, you are going to get convective roll clouds forming along the direction of the wind flow. Because of Lake Erie and Lake Ontario in particular, the wind often is along the long axis of the lake, and those multiple roll clouds will tend to converge into a single lake band. You'll sometimes be aided by frictional convergence along the shoreline, and once it gets inland, just everything falls apart and just dumps snow or rain east of the or downwind of the lakes. So kind of summing up, it's basically the same ingredients that you need for summertime convection. It's just that heat source that you get from the lake that's really contributing to everything. You need moisture, lift, instability, MLI, and off you go. Storm total snows across the area. The band, and you'll see this, the band moved north and south across the area for a number of days. And as a result, you sort of get this splattering of snow. Some people get a few inches, and as you get closer and closer to the multiple snow band crossings, you get upwards of a foot, 2 feet, 3 feet, in this case over 6 feet of snow. I don't want to diminish the impacts east of Lake Ontario, but they got clobbered as well. But I'm not going to focus on that for this particular presentation. Another interesting fact about lake effect bands is the lack of snow that occurs further downwind of the lake. So for example, Rochester, they barely got an inch or two out of this. So it's pretty amazing how, the distance between Buffalo and Rochester. I actually don't remember off the top of my head. It's 60 plus miles, but it's incredible how quickly the bands kind of fall apart downwind of the lakes. Other stats, the max snow that we got, there's a little bit of contention in here, but we think we got 81.2 inches, or over 6.5 feet in the town of Hamburg. That's a few towns south of the Buffalo City itself, and where we are here at the Buffalo Airport. The area here got over, I think we got over 3 feet here. And I showed you down where I live, I didn't quite get 81 inches, but I got closer to 50 plus inches. The duration for the meat of the event, the main part of the event, was 60 hours. Obviously, the title slide here from November 17th to 20th, that's over obviously a 4-day period, but the main event was 2.5 days long. Snow rate at times, we were reaching 6 inches per hour, and I already alluded to the bandwidth was about 30 miles, the inland extent 40 miles. That's obviously not including the lake over the lake band itself. Some of the impacts, the New York State Thruway was shut down, otherwise known as I-90, and a few other parts of that thruway system, what we call the thruway system. Buffalo Bills game was proactively moved to Detroit. It's a really great example of IDSS. We didn't actually tell them to move, but they realized and had confidence in our forecast that the area was going to get clobbered, and they moved that game, and it really was a great decision. There was a state of emergency declaration. There were also numerous local emergency declarations, road closures, travel bans, and the like. There were a few fatalities, mostly from snow shoveling or other snow removal services, and there were some auto accidents with that. I think one fatality with that as well. And finally, there were a number of building issues and roof failures that went along with the tremendous amount of snow that fell across the area. Okay, so let's get into some satellite stuff. Oh, no, before I get there, I got to do this. So in order to get a lake effect band, you need a large trough over the area, and that's helped out with a long wave ridge in the western part of the country. So this is sort of pattern recognition. This is what we're always looking for. John Hitchcock, one of our lead forecasters, put this together several years ago, looking at a number of events that have occurred in 2014, 2001, 2000, and on and on and on, and just mapping out all the times where we had lake effect events with over 18 plus inches of snow. So using the NAR data, you get a pattern that looks like this. So on the right is a 60-hour forecast from the NAIFS, and you can see in a large anomalous ridge in the west, a developing anomalous trough in the roughly the Midwest, Great Lakes, Hudson Bay area. And that's usually giving us enough confidence to issue the eventual lake effect watch and warning for events that occur like this. So I find it fascinating that you have this large scale pattern, continental pattern, and you can forecast something down to, essentially a 30-mile area, but it's really all due to those narrow lakes themselves. It's hard to, on the assumption that you're going to get a west-southwest flow, you're going to get clobbered. Okay, now onto the satellite imagery, because that's what you're all here for. So this is a 4-day loop. It goes from just after the 17th, so November 18th, and goes all the way to the 21st of November. It's a composite of both the nighttime microphysics RGB and the day cloud phase distinction RGB. What you can see here, let it go around to the beginning again. Let me get it back to Thursday night, and I'll talk my way through it. So as the lake band starts, you can clearly see it in those orange colors. We get to the daytime cloud phase distinction and moves off to the north overnight into Saturday. Then a trough moves through Saturday night. It moves into this multi-band lake effect event on Sunday, and then kind of wafts to the north Sunday night as a week-ending event. So it's really neat to see, actually, particularly on Friday, just a steady state event Friday into Friday night before it finally moves to the north and starts clobbering areas to the north of Buffalo. So we'll look at this in pieces as we go through the next several slides. So just because most people are more familiar with radar, I'm going to see if I can get this resolution a little bit better and speed it up. Okay, so hopefully that's playing nicely for you. So the main event is about to occur. You got a shortwave trough that moves through and just starts pummeling the area south of Buffalo for hours at a time, 24 plus hours of heavy, heavy snow. The band starts to move off to the north, right about here, goes across the Buffalo metro area and north into Niagara Falls. Eventually, it actually goes all the way into Canada, right about here, and then blasts southward across the area as another trough moves through. And there was 5+ inches per hour as that moved across the area. So a lot of times, if you're in the band, you're getting clobbered, and if you're outside the band, it's you can clear things up fairly quickly. But it's pretty amazing when it is right overhead. Here's a still image from the VIIRS NOAA 20 pass. It's a day cloud phase distinction. It shows just a lot of really neat features that you can look at. I'll talk about this in the next few slides. You can see north of Lake Erie, you can see a west to east convective roll clouds. And then to the south of the lake band or south of Buffalo, you can see those convective roll clouds oriented from the southwest to northeast. And you can see the same type of pattern east of Lake Ontario, an east-west flow to the north of the lake band and a west to east lake roll clouds, and then southwest to northeast roll clouds on the south side of the band. There's a lot of other features you can see on the upstream side near Cleveland, on Lake Erie. You can see there are numerous individual bands, and then they converge right around the center of the lake into a single band. You can see that over Lake Ontario as well, multiple bands on the west end of the lake converging into a single intense lake band that goes across the mid part of the lake and the eastern part of the lake. All right, so I mentioned at the beginning there are 4 distinct shortwave troughs that move within the long wave pattern, and they're really hard to, one of them is hard to pick out. There's this massive one that's coming through right now. That really gets things going and has produced the heaviest snowfall rates. You can see there's another shortwave trough that just moved through. It's really hard to pick out, and then there's another one that moves through here. I'm going to point out these individually. I'm going to let it loop through one more time so I can talk my way through it. So the first one comes through about here, and that starts the first part of the lake effect event. The second one is coming through, goes across Chicago, then across near Buffalo. That sets apart another aspect of this lake effect band. There's a real weak one that moves through right about here, moves the lake band off to the north, and then the whole thing comes blasting through with a 4th lake shortwave trough. That would be on Saturday night. So I'm going to point these out individually. Just some still images with 500 millibar SPC heights from the Meso Analysis page. So the first shortwave is occurring right about this time, around 12Z on the 17th. You could see the upstream shortwave getting its act together over north of Wisconsin. Then about 12 hours later, that second shortwave, really impressive looking upstream before it moved into the area. And that really gets things going from across areas just south of the Buffalo metro area. And it lasted for a good 24 plus hours. So 21 hours later, you can see this third shortwave, very subtle in the 500 millibar height pattern, but it's there. And from this point on, the lake band starts to move off to the north. And the fourth shortwave, you can't see it yet. It's way north of the image here, somewhere in Canada. But about 33 hours later, that shortwave trough comes barreling through, and the lake band moves very quickly off to the south. So I hear a lot of forecasters, they'll look at the models and say, hey, the models are moving the lake band to the north or to the south or something like that. It's really, of course, not the models, it's the upper level pattern. And you can see these things upstream on the water vapor imagery in particular. Another way I like to look at this is with some type of dynamic tropopause chart, either in AWIPS or in this case using Alicia Bentley's charts that she has available, looking at the temperature on the dynamic tropopause. And this is just an animated GIF I put together of those 4 short waves that are moving through. I did notice this morning there's an Easter egg here. The 3 briefly changes to a 2 if you want to laugh at me. It happens right about there. Forgot to change one of the images. But you can see those shortwave troughs well upstream, working their way to the south and across or north of the Buffalo metro area. So each one of those marks a distinct change in the direction of the lake effect band. Okay. Change the resolution here if I can. Start that again. All right, hopefully this stays looping. So this is an image that I think is really interesting. If you look over Lake Erie, you can see this widening area. It looks like a V on its side. This widening area of subsidence, both north and south of the lake. And it's probably happened before, but I don't think I've really noticed it until this particular image. It was just such a striking feature to look at. And down near the surface, there is an animation that I have later on here. You can, if I forget about it, when I get to it, you can see the dew point changing as well, either lowering as the subsidence moves across the area. So essentially, you have one large convective roll cloud with subsidence on either side. So that was kind of neat to look at. So here's a combination of nighttime microphysics and the day cloud phase distinction, plus the GLM is embedded in here as well. So for this, you can see those nice orange colors at night in particular, and the lower liquid clouds with sort of the yellow and green shading, and then the higher clouds in red for this event, but at least for the nighttime microphysics. Then of course it changes to the day cloud phase distinction during the day. And also there's the steady lightning activity that's going on, particularly right east of Lake Erie, just south of the Buffalo metro area. It's just hours and on end of lake effect lightning right there. 1, 2, 3, 4, 5. Just goes on and on and on. So for those that aren't familiar, it's pretty exciting to get thunder snow. We here east of Lake Erie, we see it, several times a year. It's I don't want to say it's not exciting, because every time it happens, everybody gets, jumps up and down, but it's a lot more common east of the lakes here than it is in other parts of the country. Very cool still. All right, let me loop this one here. Oops. Hopefully that'll stay looping. So yeah, we did request 1 minute imagery over the area, and a lot of things to really look at here. So here's the one where you have those dew points, and you can see them if you follow the areas to the north of the into Canada. You can see the dew points will slowly drop with time. You can also look at, oops, try that again. You can see the dew points drop when the band goes north of Buffalo, and then you'll see them increase again from 27. They'll drop back down, and then it'll raise back up. But just the tremendous individual lake effect, convective cells that you can see here. Just phenomenal to see on the 1 minute imagery. I could look at this really all day long. The other thing that really jumps out at you, particularly as the day wears on, you can see those west to east convective roll clouds on the north side of the band, and the southwest to northeast oriented convective roll clouds basically converging into the lake band. So really nice to have the 1 minute imagery for these events, particularly if there's very little cirrus overhead, so you can actually see what's going on. So fantastic image, fantastic loop here. Speaking of lightning, this was an image that was captured by Chris Vygotsky from Vaisala. So on the right-hand side, you can see the number of lightning strokes between the 17th and the 21st of November. And then zoomed in with this inset here. A lot of the thunder and lightning that we're getting, the lightning that is oriented along and very close to tall structures. In this case, the wind towers that are along the lakeshore just south of Buffalo. You're seeing a similar instance east of Lake Ontario as well. There's a cluster of strikes that are occurring near the wind towers there. So it's kind of neat to see this this type of effect going on. There's actually another study going on. I'll touch on that later. That talks about how the climatology has changed as we've moved, of lightning strikes have changed as we've moved to developing more and more wind turbines across the area. So this was actually part of that study. It was called the Lee Project. So here's just an image getting a 3/4 inch Graupel. You need supercooled water and some type of ice production to get that charge separation. So I find it kind of funny that they're noting 3/4 inch size Graupel here, because we used to issue severe thunderstorms for 3/4 inch size hail. So obviously Graupel isn't going to do a lot of damage because it's relatively soft. But that was a pretty impressive find to actually see that size Graupel. Usually it's more of the pea or tiny pebble size. So this is a pretty large Graupel. Here's another nice animation. It's actually two different types of RGBs. One is the day snow fog RGB, and the other is the more familiar day cloud phase distinction. Personally, I tend to use the latter because it has a little bit better resolution. But they both, in this case, are showing in particular the snow cover underneath or where there isn't any snow, where there isn't any cloud cover. So really nice. Both of them are really nice to look at. Got to have a nod to NewCap's data. So we have our 12Z and 0Z soundings, but of course at 18 or 6Z in our case in the eastern part of the country, it's more like roughly 8Z and 20Z, give or take a little bit. You can get these extra satellite-based soundings. So here's one from around 8Z and a couple different snapshots, one over Lake Erie, one over Lake Ontario, and you can see that those steep lapse rates for both soundings from the NewCap's data. And finally, one more image here, or set of images. This is after the event, and you can see the VIIRS, really nice high resolution polar orbiter imagery. You can see the change in the amount of snow that was across the area where it melted first and where it remained. Again, looking at Rochester, you can see Rochester didn't get much of anything out of this, and Buffalo just was clobbered. Couple more shots from my backyard. Again, we didn't really intend to do this, but it's bird feeders. The first image is around 7 a.m. And the second one I think is just fantastic. It shows you this huge amount of snow on that left bird feeder. Just incredible. There was very little wind in my neighborhood, at least. So the snow was the perfect consistency to be both fluffy and allowing it to stick together. It was just perfect temperature, perfect wind. Everything was just right, such that it just covered everything. Later on in the evening and toward morning, you can see a little bit of settling. The sun comes in and starts to melt some of the snow, so you get this strange little hat that shows up on some of the bird feeders. So again, I didn't really intend this to be a time lapse, but it shows how quickly and how sticky that snow was. It also has an impact on the way we can handle the snow. This type of snow is relatively, although heavy, our snow ratios are usually a little bit higher than this. It still was relatively easy to move around compared to something like the blizzard, which was so dense in comparison. That was just dust that just accumulated. Had a quick little talk about this Lee project, or lake effect electrification. So yeah, this is kind of cool seeing the Dow with the Colorado license plates east of Lake Ontario. So they'll be producing a whole bunch of research papers probably in the years to come from at least this event. And then we have a professional photographer that took this one, John Cuco, and I just like it because this camera just captures every single snowflake that was falling. And so one of the problems that you have with snow rates that are 3+ inches an hour is really nothing can keep up. Snow plows get stuck, tractor trailers start to jackknife, and then you create these huge backups, and cars eventually end up getting abandoned. We've seen this time and time again. From an IDSS standpoint, one of the things we've done has been very proactive in trying to get the throughways in the area and the highway systems closed ahead of time, such that we're not creating situations where people are stuck on the highways for days on end. So we did do that for this event, and for the blizzard event as well. That occurred on the following month. So a lot of images. I got to give thanks to Scott Bachmeyer, Dan Bykos, Scott Lindstrom, Jarell Torres, Bill Line. They produced all of the images that you see here from a satellite perspective. The radar loop was Steve Welch from our forecast office. The NAR composites and the research was done by John Hitchcock. That GFS archive that Lisa Bentley has set up, actually she's thanking the University of Albany for allowing that to continue. Background material from Comet, the synoptic images from SPC, it's great to have those. And some of the other images from Chris Vigaski, John Cuco, the Lee project, and some of the personal snapshots, just amazing to have all this photography that we didn't used to have before. So this last image is looking down my street. You can see no one even bothered to plow themselves out. There were travel bans anyway. So the road was clear. It was kind of funny to see such a clear road and no cars anywhere. So with that, I'll turn it back to you, Dan, and be available for any questions.
Thanks so much, Dave, for a great presentation. We have some questions and comments in the chat, so I will read them off. The first one here from Sheldon Cusselson. Might be interesting to see the precipitable water values for NAR for those past 18-inch lake effect events. He noted that Buffalo Rayop PW was around 7 millimeters on November 17th into November 18th and reaching 5 millimeters by 0Z the 19th and reaching 2 millimeters by 12Z on the 20th.
Yeah, we have not done that. We stuck with the NAR composites that we've set up are 500 millibar heights, 850 millibar heights, and mean sea level pressure. We have not tried looking at the moisture content. So yeah, I'll go ahead and dig into that and see what we can come up with. Thank you.
Okay, that's kind of related to Sheldon's second question. He said, would hourly satellite-derived precipitable water be helpful for forecasting heavy snow during these lake effects events. And yeah, it sounds like you'll look into that in the future.
Yes.
Okay, another question from Bridget DeRosa. In slide 19, in the subsidence north and south of the lake effect band solely, is the subsidence north and south of the lake effect band solely subsidence, or is it influenced by outflow similar to severe convection?
You know, I don't know the answer to that. It looked a lot looked a lot similar to severe convection. I'm making an assumption that it is a effectively large horizontal roll convective cloud band with subsidence on either side. But yeah, it looks a lot like what you'd see for a severe weather event.
Yeah, and I think those obs you showed showed the divergence, kind of classic with the earlier conceptual model that you had there, talking about the divergence north of it, and the obs really showed that as well. So yeah, I think it is subsidence, compensating subsidence all around that area of very strong convergence. Oh, okay. At this point, I'll ask if there's any other questions or comments for Dave.
Dan, I have a question. I have a question for Dave. This is Scott. So when I think of lake effect, one thing I think of is wind, because there's wind coming along the lake, and yet you had these pictures of your birdhouses where there apparently wasn't any wind because the snow was falling straight down. So I'm just kind of curious, when you have the strong wind over the lake, what's preventing the wind from penetrating inland?
Okay, so the image that you see here is, again, sort of my neighborhood, and the snow, there was very little wind here, and I'm about, I don't really know, let's say 10 miles away from the lake, as far as the crow flies. That's a guess. Near the lake shore and over in open areas where there was less friction, there was some wind. In fact, when the lake band was moving around on the outside edges of the lake band, you can get 20 or 30 mile an hour winds. In one case, I believe we got almost up to 50 miles an hour at the Buffalo airport. So as the band moves across the area, there are times when you're going to see stronger winds, but it's shorter duration events rather than the blizzard that we received in the subsequent month. So
are the strong winds then just on the edges of the band, and within the band itself you have lighter winds? Is that what you're saying?
To some extent, the answer is yes. Now, not in all cases. For this one in particular, again, this particular area that I'm showing a picture of in this last slide is somewhat in a valley. We're near one of the local rivers in the area, so there's a little bit more going on here than meets the eye. But
right.
There are areas that are less prone to wind across Metro Buffalo than others. That is another factor. There was wind for this particular event.
So you chose a house that didn't get a blizzard. Well done.
Thank you.
Another question from Jarrell Torres. Are you familiar with the snowfall rate or merged snowfall rate products, satellite radar data? They can be accessible in AWIPS per request from users.
I am, Jarrell, and I received a bunch of images indirectly from you for snow rate, and I did not display those. I had a lot of difficulty trying to figuring how we could use those operationally, because the way it's set up, and correct me if I'm wrong, you can unmute yourself maybe. It's you have some polar orbiter passes, and then you have the MRMS data, and it was kind of like seeing the lightning data. It's flashy and more distracting than helpful at the present time. If maybe there's something else that can be done down the road. But that was one of the reasons why I didn't display it. I know it's available.
Okay, any other questions or comments for Dave? Oh, I see some more here. Jarrell will follow up, and Brian Mata asked, was satellite used to track the snowmelt after the event? Was there any flooding post-event?
So 8 years ago, 2014, we had a November event that was very similar to this particular one. And we had a very striking warm-up after that. We were initially concerned for that event back in 2014 that there would be flooding problems, and there weren't any. As we got closer and closer to the event, we got more and more confident that we weren't covering enough of the hydrologic basins to produce a rapid rise in any of the local streams and rivers that are across our area. So as this event happened, it was almost mirroring it identically in terms of the following warm-up. Within a week, all the snow was gone. And surprisingly, there wasn't any significant flooding that occurred. And we think that's because of the fact that it's, again, so localized. While I'm showing, in the case of this particular image, 50 some odd inches of snow across the area, most of the area across these hydrologic basins don't see that nearly as much snow. So you can think of it as a one overwhelm the river basins. So that's kind of what happened here. We had a tremendous localized event, striking warm up. The snow was gone in a week and no flooding, at least for the Buffalo metro area.
Okay, any other questions or comments? All right, at this point, we'll conclude today's webinar. And once again, thank Dave on a great presentation.